here.
I am indeed. Hello. Delighted to be here. So I'm going to follow from Bash's example. I'm going to give you a bit of a flavor of the problem that we were looking at over summer, and then I'll talk a little bit about what FDL actually is. So we want to look at a couple of different challenges. As Anne earlier alluded to, this is the second year we were looking at this particular problem. And the first sort of direct use case is how can we ensure effective space traffic management? And the way in which we wanted to go about that was trying to understand how EUV, this extreme ultraviolet, might have an impact on atmospheric drag. So in this slide, you'll see there's actually a whole bunch of things that can impact, funnily enough, our Earth in the Sun-Earth system. And we're attempting to look at how these extreme instances of ultraviolet might actually impact our upper thermosphere. So in the next slide, you'll see there's this equation where if we keep going on the slide, you'll see there's all these different coefficients and components and necessary parts. And what we're most keen to understand is this atmospheric density, which is here as this rho. And a lot of the rest of this is extremely hard to sometimes find, these satellite drag coefficients and all the rest, but they are determined and they are found. But the greatest uncertainty exists on this atmospheric density value. And as you can see from that little diagram, there is this drag that occurs. And we want to make sure that we can understand this the best, again, for, say, predicting a whole bunch of, well, sometimes rubbish, sometimes satellites, important things, up in our hemisphere. So what we're trying to do is increase what's called the Goldilocks zone for these low Earth orbiting satellites. So there's currently a zone that's reasonable, where we can sort of not have too much uncertainty in drag, and also there isn't too much debris already out there, and a whole bunch of other considerations for what current satellites are there. But we're trying to expand that by reducing this uncertainty. And what we were doing, again, to Anne's earlier point, was taking all these lovely data coming from ARD, which is another team on the project, and using it through something called SDOML, which are these beautiful images in the middle, which is coming from the SDO platform, Satellite Dynamics, Solar Dynamics Observatory platform. And we were trying to use all this beautiful imagery to better understand thermospheric drag with the prior work, which was Carmen in this case. So what we did is we encoded the sun, i.e. we took these images and built better embeddings so that it was a bit more accessible, a bit more usable for the ML community, and certainly sped up a lot of our training and obvious inference times downstream for our later models. And then we actually had some interesting results from that. So you'll see as we move on, we sort of wanted to build all these different versions of these models, partially to improve the sort of baseline. So there's the sort of SOTA, state of the art, currently, which are these typically sort of operational empirical models, many of them physics informed. And then there's those from purely ML. And what we wanted to do was find a way to either mix these or to improve the ML such that we've incorporated a lot more understanding from the physics informed, i.e. actual physical information of what's occurring in these interactions. So we ended up expanding. So sorry, it's not the best diagram, but the second box there was the expansion of the original model to improve direct EUV, using the direct EUV inputs and the actual using of this standard empirical model work. And then, sorry, yes, I wanted to provide an example of something that went wrong, and that was our overcoming the problem within the data. And this was just funny. I have to put the slide up each time because I don't know if you've noticed, but there's something very different about that periodic motion than the rest of it. And that's because, weirdly enough, for one particular orbit, one of the accelerometers seems to go out to an end, an overflow issue. And all of a sudden, when we started cleaning that up, we managed to massively improve model performance. So this was just an example of finding something that exists in a public data set that had the systematic anomaly that we were able to sort of spot throughout this work, and fixing that after a couple of weeks of scratching our heads was quite beneficial, as you'll see in the next slide, where we can drop by I think it's 9 percentage points on average percentage error. So point being, we learned throughout this experience that SDOML can actually replace a lot of these proxies that actually occur at these very shorter sampling rates than the past. And we actually also learned that this approach, this particular model and this particular way of going about incorporating this EUV actually is better and models better in these periods of high solar activity, i.e. times when we know less about what's going on typically because we've seen less of it, but we can actually include these as higher cadence proxies and actually to better understand in these weirder, sort of stranger cases. So at the end of the day, the end of the project, which is again, like everyone else has mentioned, not really over. We're still playing with it. The example we took, which was the worst case, this geomagnetic storm, you can see that we ended up with this higher cadence proxy data set, as well as these compressed embeddings, making that accessible to the ML community and space weather community, and then the ability to do much more accurate thermospheric density prediction. And this will be one of the next projects, and yeah, getting that last 10% of uncertainty would just be amazing, because it's getting there, and we had a bit of a jump this year, but we're still trying. So finally, I wanted to talk a little bit about actually my experience in FDL rather than just the project, and effectively I just wanted to include that we had phenomenal just access to so many incredible experts. I mean, that the way in which I sort of learned about it is within the sort of machine learning communities, as I'm sure many of you might be from, if not space weather communities, sort of talk about FDL, and I found out from a postdoc and was sort of unsure, but then learned this is exactly what I wanted to go do, because you just get to spend a summer building stuff. It's like a hackathon on steroids for much longer. And the people that you get to talk to are, I don't know, was it technical director of AI at Google, which was Massey earlier. I think he's the inventor of QuickTime, Jonathan Knowles. Like people who you would never otherwise like immediately think to get access to, who you can just ask questions and honestly just talk to and try to understand how best to solve this project. So on top of all of that, you then, unlike, I don't know, there are probably some PhD students probably on this call who don't have access to a huge amount of compute, and I'm privileged to have access to some, but not nearly the amount of compute that was on this particular project. I mean, over summer, we weren't just using two DGXs, big computers from NVIDIA, but we were in NVIDIA's Slack channel talking to them. When things weren't working, we just talked to them and they would help us figure this out. Like it's not the same as a traditional, say, academic project. It's you're actually with the people who are desperately trying to get this working as well, and everybody involved. And it's a phenomenal way of going at a problem. And it was a huge amount of fun. I had all these wonderful people around me, as you can see on the screen. And I would just add that, like, if you're interested in joining, it's really the people as well as the opportunity to do this awesome, crazy, very, very intense summer project. Okay, that's me.